London, January 11, 1935. The Royal Astronomical Society is holding its monthly meeting. Room is full. Professors, astronomers, and most respected scientific minds in Britain. A 24-year-old Indian scientist stands up and presents his work, 5 years of calculations, a complete theory of how stars die. He finishes, there's a polite applause. Then the most powerful astronomer in the world walks to the podium and he dismantles him, not quietly, not privately, which he had privilege of, but in front of everyone. His name was Arthur Stanley Eddington, and the young man he destroyed was Subramaniam Chandrasekhar. But here is what makes this story strange, what makes this story worth our time. Chandrasekhar was right all along, and Eddington, brilliant, decorated, universally admired scientist, was wrong. It would take decades for the world to fully admit what Chandrasekhar had seen. To understand what happened that day, you have to understand what Arthur Stanley Eddington meant to science in 1935. This was not simply a famous man. This was the man who had confirmed Einstein's general relativity. In 1919, Eddington sailed off to the island of Principe off the coast of Africa, observed a solar eclipse, and proved that light bends around mass, exactly as Einstein predicted. He made Einstein a household name. He was, in many ways, the guardian of modern physics. When Eddington spoke, the room did not just listen, it deferred. So, when a 24-year-old researcher from Madras, India, arrived in Cambridge with a new theory, a theory that Eddington found uncomfortable, the power dynamic was not even close to equal. When scientists first saw this white dwarf, Sirius B, they were puzzled because this star was so dense and so massive, like the mass of Sirius B is as big as Sun. However, its size is just about the size of Earth. So they were thinking, like, what has stopped this star, the gravity in this star, from pulling everything inwards and stopping at that size? To understand why Chandrasekhar's discovery was so significant and why Eddington found it so threatening, we need to go somewhere unusual. We need to go inside a dying star. A star, at its core, is a war between two forces. Gravity pulls inward always, relentlessly. The mass of a star, hundreds of quadrillions of tons, all of it pulling towards the center. Against it, the outward pressure of nuclear fusion, hydrogen burning into helium, releasing energy in every direction. For billions of years, these two forces hold each other in perfect balance. The star shines. But the fuel runs out, and gravity, which has been patient for billions of years, finally wins. Now, when the last of this fuel is gone, the star begins to collapse. The outer layer falls inward, temperature plummets, and what you are left with is the matter under extraordinary compression. Not ordinary compression, not the kind you feel when you press your hands together. We are talking about densities that have no equivalent in human experience. A teaspoon of white dwarf material weighs as much as an elephant. So the question that defined stellar physics in the 1920s was this: when a matter is crushed to that kind of density, what holds it up? Not heat, the star is cooling; not fusion, the fuel is gone. So what prevents the star from simply collapsing further into nothing? When scientists first saw this white dwarf, Sirius B, they were puzzled because this star was so dense and so massive, like the mass of Sirius B is as big as Sun. However, its size is just about the size of Earth. So they were thinking, like, what has stopped this star, the gravity in this star, from pulling everything inwards and stopping at that size? The answer came in 1926, and it came from quantum mechanics. Rolf Howard Fowler was one of the finest theoretical physicists in Britain. He applied to newly formulated laws of quantum statistics, specifically the Fermi-Dirac distribution, to the dense matter of a dying star. And what he found was elegant and for a moment complete. Here is the key idea. In quantum mechanics, there is a rule, a hard rule, not a guideline, not an approximation, a hard rule, a fundamental constraint built into the architecture of reality. Two electrons cannot occupy the same quantum state at same time. Not approximately, not usually, never. Now imagine what this means inside a dying star. As the star collapses, electrons are forced closer and closer together. They are being pushed into increasingly small space. And because no two electrons can share the same state, each electron must carve out its own unique position, its own unique momentum. As the space shrinks, the electron runs out of slots, and the only way for an electron to claim a unique slot when all the nearby slots are taken is to move faster and faster, not because it is hot, but because the rules of quantum mechanics force it to move to find a state that hasn't been taken. This movement creates pressure, real measurable pressure, pushing outward against gravity. Fowler called it degeneracy pressure. And here's the critical thing about Fowler's version of this pressure. In his non-relativistic treatment, where the electrons are fast but nowhere near the speed of light, there is a clean mathematical relationship. The pressure is proportional to density raised to the power of 5/3. You don't need to feel that number deeply. What you need to feel is what it means. It means harder gravity squeezes, harder electrons push back, always without limit. Squeeze harder, they push back harder. Squeeze harder still, they push back harder still. The electron pressure is infinitely scalable. It can match gravity no matter how heavy the star is. Fowler's conclusion followed cleanly from this. Any star of any mass could become a white dwarf. Gravity would compress it, quantum pressure would halt the collapse, and the star would simply sit there, cooling across billions of years, glowing faintly into dark. A gentle death available to every star. Eddington found this deeply satisfying. The universe was tidy. The puzzle seemed to have solved. So look at this. Electrons provide some sort of pressure, this outward pressure that fights against gravity. And so a star becomes a white dwarf and be at that size till the end of its life. But it was thought that this would be the end of all the stars, no matter their size or mass, will end up as a white dwarf, which of course isn't true. But there was an assumption hiding inside Fowler's calculation, a small one, so small that Fowler hadn't thought to question it. He had assumed that electron was moving slowly, slowly enough that ordinary rules of mechanics applied, not the rules of special relativity. Chandrasekhar asked, what if that assumption is wrong? On a ship to Indian Ocean 1930, 19-year-old did calculations that Fowler had not done. He did not challenge Pauli's exclusion principle. He did not challenge Fermi-Dirac statistics. He accepted all of it. He simply asked one additional question. If a star is massive enough, the densities involved are enormous, and at the enormous densities, the electrons are forced to move faster and faster to find unique states. We established that, but faster has a limit. There is a speed. The universe will not allow anything to exceed the speed of light. And as electrons are compressed into tighter and tighter spaces, forced by Pauli's exclusion principle to move faster and faster, what happens as they approach that limit? Special relativity is very specific about this. As an object approaches the speed of light, its mass, its effective inertia increases. It becomes harder and harder to accelerate further. The closer you get to the speed of light, the more energy you need to go just a little faster. In other words, electrons hit a wall. Not a physical wall, but a mathematical one. A wall built into the structure of space-time itself. In Fowler's non-relativistic world, the pressure scaled as density to 5/3. Squeeze harder and you get more pushback. In Chandrasekhar's relativistic world, where electrons move close to the speed of light, the pressure scales as density move to 4/3. 4/3 versus 5/3. 1/3 difference is an exponent. That sounds almost trivial, but it is not. Here is what the difference means in plain language. In non-relativistic case, the pressure grows faster than gravity as the star compresses. It always catches up. Balance is always reachable. But in relativistic case, the pressure grows slower than gravity as the star compresses. It cannot keep up, and past a certain point at a critical density, the gravity simply outpaces whatever electrons can provide. The electrons are already moving near the speed of light. They have nothing left to give, and gravity wins. This means something extraordinary. It means that star cannot stop collapsing at the white dwarf stage. It has gone too far. The quantum pressure that would have saved the lighter star, that did give lighter stars throughout its history of the universe, is insufficient. The star must go somewhere else, somewhere the physics of 1930 did not have words for. Chandrasekhar's analysis was this, that there is a limit to this degenerative pressure provided by electrons. After a certain point, this movement, the speed of electron, gets very close to the speed of light. This would mean that electrons would require more and more energy to move. That would mean that essentially it will stop moving, it will stop providing that pressure, and then it will collapse and then become something other than white dwarf. Chandrasekhar presents his work calmly and clearly. The critical mass, the different densities of stars depending on where they fall relative to that limit. The mathematics is watertight. And then Eddington takes the podium. He begins with a joke. I do not know whether I shall escape from this meeting alive, but the point of my paper is that there is no such thing as relativistic degeneracy. Laughter, polite laughter. And then, in front of everyone, Eddington dismisses Chandrasekhar's entire framework. He calls the theory illegitimate. He uses the language of Victorian moralist. The formula is based on a combination of relativity mechanics and non-relativity quantum theory, and I do not regard the offspring of such a union as born in lawful wedlock. And then one of the most extraordinary sentences in the history of science. I think there should be a law of nature to prevent a star from behaving in this absurd way. Then he leaves the podium. The president of the society prevents Chandrasekhar from responding. The argument, he says, will need to be carefully weighed. Chandrasekhar's analysis was this, that there is a limit to this degenerative pressure provided by electrons. After a certain point, this movement, the speed of electron, gets very close to the speed of light. This would mean that electrons would require more and more energy to move. That would mean that essentially it will stop moving, it will stop providing that pressure, and then it will collapse and then become something other than white dwarf. His own competing theory. Naturally, Chandrasekhar was furious. He wrote to the physicist Leon Rosenfield, a close friend working with Niels Bohr. He asked for an authoritative statement. Someone like Bohr, Paul, or Dirac needed to say clearly that Chandrasekhar's physics was sound. Rosenfield's reply came back, and it was one of the most quietly devastating things in this story. He wrote that nobody had ever dreamed of questioning these equations, Chandrasekhar equations, that Eddington's objection was utterly obscure, that Chandrasekhar should cheer up and not let himself be scared by high priests. Rosenfield confirmed that physics was correct. There was no error. But in Paris, months later, at the International Astronomical Union, Eddington returned the attack. He called Chandrasekhar's work a simple hearsay. The president again refused Chandrasekhar a right of reply. Paul Dirac privately confirmed the physics was right, and so did others. And yet, nothing changed. Not for decades. Chandrasekhar made a decision. He did not fight. He did not campaign. He moved on. He left stellar structure entirely and spent years producing groundbreaking work in other areas: mathematical theory of black holes, radiative transfer, fluid dynamics, field after field. He arrived at a level of mastery that few scientists ever reach in a single lifetime. But the limit stayed with him, and slowly the universe began to confirm it. In 1967, neutron stars were discovered, the dense, spinning remnants of massive stellar collapses, exactly the kind of object Chandrasekhar's limit had implied must exist. Black holes were confirmed. Universe was doing the thing Eddington has said no law of nature would allow. In 1983, 48 years after that meeting in London, Subramaniam Chandrasekhar was awarded the Nobel Prize in Physics for the work he had done on a ship in 1930 for the equations that Eddington had called illegitimate. In 1999, NASA launched a space telescope dedicated to observing X-rays from the most extreme objects in the universe: neutron stars, black holes, supernova remnants, objects that exist precisely because of the limit Chandrasekhar discovered. They named it after Chandrasekhar, Chandra X-ray Observatory. So here's the question that this story leaves us with. It's not about Eddington being wrong. Every scientist is wrong sometimes. The question is, why did authority matter more than evidence for 5 decades? Chandrasekhar's mathematics was not refuted. It was not disproved. It was dismissed. And the scientific community, which prides itself from being immune to prestige and power, allowed one man's certainty to delay a fundamental discovery for a generation. This is not a story about a villain or a hero. It's a story about how even the most rigorous systems of human knowledge are shaped by human things, by status, by elegance, by the discomfort of conclusions that feel too strange to be true. Eddington could not accept that a star might collapse a few kilometers in radius. It seemed absurd. It violated his intuition about what nature ought to be like. But nature doesn't care about our intuitions. It does not ask for permission to be strange. And there is something quietly extraordinary in that. The universe will do what it does: compress stars beyond imagination, create objects so dense that even light cannot escape, regardless of whether the most brilliant mind in the room approves. Chandrasekhar understood this. He kept working, he stayed quiet, and he let the universe speak for itself. And decades later, it did. Thanks for watching. And the question we have to sit with is this: what happens to a true idea when the powerful person decides it cannot be correct? To understand Chandrasekhar's discovery, we need to start with a puzzle. A star is, at its core, a war. On one side, gravity, the relentless inward pull of all that matter. On the other hand, there's outward pressure of nuclear fusion, hydrogen burning into helium, releasing energy in every direction. For billions of years, these two forces hold each other in perfect balance. The star shines, but the fuel runs out. This nuclear fusion fuel runs out eventually. And then what? And this was a puzzle till half of 20th century. By the early 1920s, astronomers had discovered something extraordinary. They found stars that were impossibly dense. A star called Sirius B, the companion to the brightest star in a night sky, had a density of 61,000 grams per cubic centimeter, or in other words, 1 ton per cubic inch. Let this sink in. A teaspoon of this material would weigh as much as an elephant. Now, Eddington himself dramatized this discovery. He called it the dense matter puzzle. How could something so compressed even exist? When a normal star cools, matter should return to ordinary densities. But Sirius B was clearly not cooling. It was stuck. Then, in 1926, a physicist named Ralph Howard Fowler found the answer. Using his new tools of quantum mechanics, he showed that the electrons in a dying star could provide kind of a pressure, not from heat, not from burning,